Good morning, everyone. This is Rajan Raval, representing IBPSA Education Committee. I welcome all of you from various parts of the world who has joined this webinar. As you know, that this webinar series is based on IBP's special edition, which is on simulation and users. And I'm very, very glad that Nathaniel Johns has agreed to offer this webinar on air lighting, and primarily the title, as you can see it on screen, is effects of real-time simulation feedback on design for visual comfort. Nathaniel is at Arup in the Bay Area, San Francisco office, and I think the work which he has done along with the MIT lab. During the question and answer session, which would be the end of this presentation, we do expect Christopher Renard to join us, but in any case, we will have question and answer sessions with Nathaniel. Those who wish to ask question should use a question pane and should type the question, and I will moderate the Q&A session at the end of this webinar. I again thank you, Nathaniel, for offering this webinar, and welcome all of you. I will hand it over to Nathaniel.
All right, thank you. My name is Nathaniel Jones, and this is a presentation based on the paper that was recently published, Effects of Real-Time Simulation Feedback on Design for Visual Comfort. This is work that I developed as part of my dissertation at MIT, together with Christoph Reinhardt at the MIT Sustainable Design Lab. And we were trying to address the question, how can simulation be an effective design tool? I want to start off framing this question by describing the way that we use simulation today in building design. And frequently that means the designer works on progressing a design for quite a while and then hands it off to someone who will perform a simulation analysis of that design. Often that analysis is done by another group, another office, or even another company, and then handed back after some time to validate the design. And we've often remarked how we'd like to see a more iterative approach to building simulation analysis, so that each time there was a change to the design, it could run through a set of analysis and provide immediate feedback to the designer moving forward. We believe that speed of interaction is important to achieving this mode of work. There's been a fair amount of analysis done of speed of interaction, and what I'm showing now is one of many studies that were done at IBM back in the 70s and 80s. The question they were looking at was, how does the speed of a computer affect the productivity of its user? And they framed that as the question of system response time. System response time describes the amount of time between when you give a computer an input and when you receive an output from it. And what they discovered is that there is a relationship, for instance, as shown in this graph, between the productivity of the user and the speed of the computer that the user has access to. And that increase in productivity with a faster response time is greater than just the reduction in time waiting for the computer. It actually means that the user is working and thinking faster as well. They also discovered in another study that an expert user faced with high system response time was not as productive as an average user using a low response time system. I want to turn now to Alan Newell's Unified Theories of Cognition. This was a book that described methods of interaction with computers. So it's really cognition of people when they're using computer systems. And he classified a number of different types of interaction that people had with computers based on the amount of time that the person needed to think about that action. Some later authors, Leo and here, gave us a better defined classification of that work, and they described things as deliberate acts, things like using a mouse or trackpad keyboard where there's not really any thought that precedes the action. Or cognitive operations, things like asking a question, giving a command, where the thought feeds almost immediately into the action. And finally, unit tasks. These are more systematic, more strategic thinking, where there might be some amount of time, 1 to 10 seconds, between starting to think about the question about how to approach some problem and then actually carrying out that solution. Recent work has suggested that there's some fluidity between these types of thinking, and that depending on the interface we're using, we can move someone toward thinking in terms of cognitive operations or thinking in terms of unit tasks. So for instance, if I present you with an online game where the system responds quickly to your actions, you may approach that game through cognitive operations, through lots of interaction with the game. Whereas if the game is slowed down because of a slower machine, you may think in more strategic terms and approach the game very differently. Or if you're performing web searches with a fast internet connection, you may perform a large number of web searches trying to narrow down the thing you're looking for. Whereas if you have a slow internet connection, you will think more strategically about what to search for and perform fewer searches. Lewin here developed these classifications according to the amount of time that these operations took, and through their study suggested that there's a point at which interactivity occurs. That is when interaction takes less than half a second. And so our goal has been to try to reduce the amount of time it takes to get back information about building performance simulation to that half-second mark. Now I want to step back and look at the problem that we face in doing daylight simulation in buildings. I'm showing here the results of 2 simulations of the same model with nearly the same parameters. One is what I call an accurate simulation that took about 49 minutes, and the other one is a fast simulation that ran in 1.5 minutes. And the only real difference between these is the amount of time that was spent searching for paths that light can reach to the camera. That's searching for paths by shooting rays into the scene. These are shown in false color, which makes it more apparent how much light is in each part of the scene. And if you as a designer were to try to make decisions based on the fast result that found less light, you might be tempted to make larger windows, which could expose this room to the possibility of overheating and glare. But we know that we want these fast simulations, and when we look at the amount of time that a user spends on a model, we can see how those different lengths of simulations would fit into an existing workflow. So this is data that was gathered from one architect over the period of about 3 hours working with the tool Rhinoceros. Each dot represents one interaction between the user and the computer, and the height of the dot on the vertical axis indicates the number of objects in the model that were altered through that action. You can see in this model, or in this timeline, that there's really only one point at which the architect could have run that 49-minute simulation to get an accurate simulation result in this building, and that was during the period when the user took lunch. But there are plenty of times when you could run a 1-minute simulation or shorter in this workflow. So how do we make our simulations faster? For a long time, the answer was through Moore's law. Moore's law says that the density of transistors on a computer chip roughly doubles every 2 years. For a long time, clock speeds on computers, that is the speed at which the computer performs operations, also increased at about that same rate. That all changed in about 2004. At that point, clock speeds leveled off. We continued to put more transistors onto our computer chips, but we used them for something else. And that was to put more cores onto a chip. So now we have 2-core, 4-core, or even 16-core computers available to us. These are the 2 computer chips that are in my computer at home. One is a 4-core CPU, and the other is one of the latest GPUs that has over 4,000 cores, in addition to 72 dedicated ray tracing cores. So if I really want to parallelize my work to get lots of speed out of it, I'm going to do that by running things on the GPU. So starting about 5 years ago at MIT, I started to release programs called AcceleradRT. These were versions of the existing radiance tools, which is the industry standard for doing lighting and daylighting simulations in buildings, but parallelized to run on the GPU. And I showed through several publications that these simulations could be 30 to 50 times faster than the equivalent simulations carried out on the CPU with the industry standard tools. But that doesn't really get us to a real-time simulation. So we had to do more to get to real-time. And so about 2 years ago, I introduced a new tool, AcceleradRT. RT stands for real-time, and it works a bit differently. So in the older ray tracing tools, we would use something called distribution ray tracing, where each time a ray hits a surface, it sends out a number of new rays to investigate how much light can hit that part of the scene. AcceleradRT uses path tracing. It still sends out a direct ray to see how much direct light hits each part of the scene, but then it also sets out a set of random rays that sample the diffuse lighting, and it can send those out one at a time, creating a sort of animation. So if we look at that animation over time, here are a set of frames from one animation. Frame 0 is only the direct component of the lighting, and then with each subsequent frame, we add in a portion of diffuse lighting until at the end, by the 10,000th frame, we get something that looks very similar to what radiance produces. Now, although we didn't need to wait that long to get an image that looks really nice, we can get back data about this space much sooner. In fact, even by the 10th frame, we have very good readings on the overall illumination and the probability of receiving glare in the space. So we believed that by doing this, by producing fast simulation results, we could make a difference in how people designed. But we didn't know of any work that had tested that hypothesis. So that was the goal of this experiment, to find out if faster tools make a difference to design. And to do this, we created an A/B test where users would be faced with two different tools and attempt to do a similar design problem in each one. The first tool was DIVA, which is a tool in common use for producing daylight simulations. And the users were working on this building, which has a number of desks in a daylit corner office space. And they could produce simulations through the DIVA interface, which is shown in the upper left corner here. The other tool was AcceleradRT, which I'm showing in this video. AcceleradRT consists of a window that shows the current view with false color, and also a dial that shows daylight glare probability. The user was able to select different shading options. Similar shading options were available both using Accelerad and using DIVA. But in Accelerad, because it has that real-time interface, they're able to see the results of adding a shading device immediately. Then they're able to move around the scene and verify that different shading devices, verify how well different shading devices work for different situations. They could also change the time of year, the time of day in both tools to make sure that they came up with shading designs for this space that worked well under all conditions. Now I'm going to digress a little bit and talk about the things that we look for in designing a visually comfortable space, which they were tasked to consider with both tools. There are really three things that we consider for visual comfort. One is the presence of discomfort glare, which is to say that you have sun or other bright objects in the field of view. When discomfort glare becomes extreme, it becomes disability glare because it prevents us from being able to do work. The second time is veiling glare. That's unique to working with screens and other reflective objects, where light hitting the screen will cause a reduction in contrast on the screen, making it difficult to see the image on the screen. And finally, there's dim lighting. It may still be possible to see digital work on a computer screen, but it becomes difficult to do manual tasks on the desk. We have ways of analyzing each of these forms of visual discomfort. For glare, we tend to use a metric called daylight glare probability. This is recognized as one of the most accurate ways for assessing glare in spaces because it considers both the brightness of the overall scene and also the contrast between the average brightness in the scene and the brightest objects in the scene, those that are likely to cause glare. It also rates glare sources according to their position in the field of view. So glare sources closer to the center of our field of view are weighted more heavily, whereas those toward the periphery that are affected by features of our face, such as our nose and brow, or by the reduced number of rods and cones in the extremities of our retina, will have less importance. Contrast ratio is a little bit simpler to assess. We can look at the difference in brightness between the bright and dark pixels of a computer screen, and consider also the reflected light off of the computer screen to produce a contrast ratio. We can also define a minimum contrast ratio based on the overall brightness of the scene. And finally, for determining if the space is bright enough to work in, we tend to use a cutoff of 300 lux in the United States, which is the minimum brightness that we would want for office tasks. This is also something that we can represent spatially to see what parts of the space achieve that daylight autonomy that is reaching 300 lux and for how much time. And we have a spatial metric which says that we want to achieve at least 300 lux in at least 50% of the occupied parts of in the occupied times in that building. And we call that the spatial daylight autonomy, or SDA, 300 lux at 50%. For this task, we simplified this a bit. Rather than trying to make our users calculate each of those things, we gave them some rules of thumb. We said that they should try to keep the daylight glare probability less than 35%, which is a typical standard. In order to combat veiling glare, they should keep the amount of light hitting computer screens less than 50 candela per square meter. And in order to have enough work surface luminance in our model, they should try to keep at least 48 candela per square meter on their desktops. As some examples, here's a comfortable view generated by DIVA, where the overall daylight glare probability is 25%, which is acceptable. There's minimal light reflecting off of the screen, and the desk is sufficiently bright to work on. Beside it is an uncomfortable view, where there's 100% daylight glare probability due to a direct view to the sun in this image. There's too much light reflecting off of the screen. The desk is sufficiently bright. It's difficult to come up with a view where you have both too much light on the screen and not enough light on the desk. So given these tools, what happens to the user behavior? To start out with, here's an example of one user using two different models. In AcceleradRT, they had a model cited in Minneapolis, and in DIVA, they had a model cited in Albuquerque. That was to make sure that they wouldn't try to use the same strategies in both models and learn from their first model in developing their second strategy. What you can see immediately is that the user using AcceleradRT explored more of the space. The thickness of the arrows represents how long they spent examining the view at each position. Using DIVA, they did much less exploration and tended to stay facing the same view for most of the time. We can also aggregate all of the user's data and see what parts of the scene they explored and for how much time. In this view, the brightness of each of the triangles, each of the wedges, represents the amount of time that the users spent examining, that the users in total spent examining that view. And again, you can see much more exploration happening with Accelerad compared to DIVA. We could also examine each user's timeline to see how often they performed actions with the tools and when. Here I'm looking at just 5 of the subjects. On top, their timelines using DIVA, and on the bottom using Accelerad. And you can see very different characteristics between the two tools that turn out to be similar for all of the users. In DIVA, they have more of a punctuated method of working, where they make one change, run a simulation, and then make another change. There's also a fair amount of time that follows each simulation when they examine the results of that before they make their next change. In Accelerad, there's a much more constant workflow. They make many changes. They see results at the end of after each change, which is why we don't show the simulation runs as points on the Accelerad timelines. But it's a much more constant method of working. This suggests to us that there is a different mode of thought involved when using the faster tool. And when we sum up the number of interactions that they had with each of these tools, we can also see much more exploration of date and time, of shading devices, and of different views using Accelerad compared to using DIVA. We also had to consider that it took a different amount of time to get results from each. From Accelerad, we believed that after the user had about 2 seconds in each view, they could have deduced some result from that and moved on to the next view. In DIVA, it took about 20 to 30 seconds to get a simulation result after starting a simulation. So here I'm showing the number or the fraction of states that each user looked at in which they spent a certain amount of time. So for instance, using Accelerad, for 25% of the views that they looked at, the users would spend 5 seconds or more looking at those views. Now, to try to make these two displays more even, I'm going to shift over the DIVA curve in order to get it to line up with the Accelerad curve after the simulation would have finished, to show how much time the users spent looking at a result after it finished. And you can see that if the users had been using the same method of thought, we would have expected these curves to line up now. In fact, users tended to spend more time looking at a result after the simulation finished using DIVA than using Accelerad. And that again suggests to us that there's a different method of thought involved here. Our next question is, how does that change affect the quality of the designs that were produced? In order to examine this, we wanted to investigate the quality of the design under all lighting conditions, not just the ones that the user might have had a chance to look at. For the question of the brightness in the scene, whether or not there's sufficient lighting to do work, we already have that spatial daylight autonomy metric, which we can use to study that. But we didn't have an equivalent method of studying glare. So in this study, we developed a new tool, or a new metric which we could use to assess the overall glare likelihood in a space. We call that the spatial annual enhanced simplified daylight glare probability, which is based on the faster enhanced simplified daylight glare metric, which allows us to run simulations for the entire space in a reasonable amount of time. We're talking about running glare simulations for the space in days and generating about a terabyte of data in all in order to come up with a comprehensive metric for the amount of glare in each of these spaces. Essentially, we're considering all points in the space for 8 view directions at each point at all occupied hours to see how many of those points achieve the desired daylight glare probability less than 35%. For the 2 models that we had users studying in this study, we then graph the daylight glare probability and the spatial daylight autonomy for each of those models. Now, our ideal would be to have 100% spatial daylight autonomy and 0 daylight glare probability, which would put us in the lower right-hand corner of each of these graphs. Of course, that's not possible. There are no designs that produce full spatial daylight autonomy while completely eliminating glare. But we want to be on the lower right-hand curve of each of these. That's the curve which is called the Pareto frontier. The triangles in this graph represent designs that were actually chosen by users, and the darkness of the triangle represents how many users chose that solution. The diamonds represent the same for DIVA. What we found is that 60% of Accelerad users chose optimal designs, whereas only 40% of DIVA users chose optimal designs. That's a significant difference between the likelihood of choosing an optimal design using the fast simulation tool as opposed to the slower one. And in case you're interested, here are the designs which were most commonly chosen by the users, and both of these designs are optimal designs. Finally, I want to address how the simulation tools affect user satisfaction. After using the tools, we asked participants how confident they felt in their glare assessment and how confident they felt in the performance of the design that they chose at the end of the study. For both questions, users were more likely to express confidence when using AcceleradRT compared to DIVA. We also asked them which tool they felt was more familiar. Now, many of our participants had already used DIVA in the past and found it more familiar. In fact, it's interesting that any of them ranked AcceleradRT as more familiar, considering that none of them had previous exposure to it. Additionally, users tended to find the faster tool more enjoyable to use, more relaxing, and more educational. And when we asked them about their overall experience, 90% of them preferred AcceleradRT overall. Finally, we want to try to understand why faster tools result in improved designs when considering glare and spatial daylight autonomy. Our first hypothesis was that it was simply a matter of having more exploration possibilities. So we looked to see between the users who chose optimal designs and the users who chose non-optimal designs, how many states each group chose to look at. That is to say, how many combinations of view, time of year, and shading device. What we found is that in both cases, whether or not the users had chosen an optimal design, they tended to look at many more of those states using AcceleradRT compared to DIVA. In fact, if anything, the users who did not choose optimal designs looked at more options than the users who did choose optimal designs. So we can't simply say that doing more exploration results in better designs. Here's one thing that does seem to help. Those users who had a background in architecture were more likely to come up with an optimal design if they were using AcceleradRT than the users who did not have backgrounds in architecture. However, if they were using DIVA, there was essentially no difference in performance between the users with and without architectural backgrounds. We could also look at the amount of professional experience that these users had. Users with 3 or more years of professional experience were much more likely to develop optimal designs than users without that amount of experience. But again, only if they had access to the FAST tool. So it seems like the FAST tool is reducing the barrier to entry for these users because they're able to develop optimal designs even as they have reduced amounts of experience. So I want to conclude now by describing the overall contributions that we made in this study that we believe will be relevant. One was to introduce AcceleradRT, a tool that's able to produce real-time simulation feedback and help designers. The other was to show a form of user testing, that is A/B testing, which allows us to compare simulation tools. And through our publication, we believe that we've created a method that others can use in analyzing other simulation tools for building design as well. And finally, we've introduced a new spatial and annual metric for daylight glare probability, which we believe can help in rating overall building performance with respect to glare. As takeaways, I want to emphasize that system response time is important for building simulation tools. Low system response times were correlated with more exploration, higher confidence, increased user satisfaction, and more optimal designs with respect to daylight autonomy and glare. Flow is an important aspect in designing tools for users. By promoting flow, that is making tasks flow into each other and become more intuitive, we can reduce barriers for entry and help people develop skills to create tasks, to perform tasks like daylight design. Real-time visualization is effective for designing for visual comfort, and it's important in general to produce real-time feedback in order to promote better design. And finally, human subject testing using A/B tests is an effective way to evaluate simulation software, and one that we hope to see increase in the future. I want to finally note that our tool, AcceleradRT, is now available for public use, and it's available for download through a website which I'll share here. That concludes the presentation I wanted to give, and I think now we'll have some time for questions. Thank you.
Yes, thank you, Nathaniel. I request the audience or attendees who wish to raise a question can send me. Yes, I got a first question from Sarah. Sarah, would it be okay if I unmute you and you can ask question? You need to type your answer. Let me. Sarah, I can't unmute you. Can you just? Okay. So Sarah's question is that what computer or laptop I need to buy to install AcceleradRT?
Sure. So I try not to make these talks too commercial. AcceleradRT is based on a proprietary ray tracing technology, which is developed by NVIDIA. So it does run on any of the recent cards that were developed by NVIDIA. My experience has been that it tends to work well on any computers that use that tool that have been developed in the last 3 or 4 years. Although with the latest tools, with the latest cards, that have come out this past year, there is additional speed up that's available now.
Thank you. Olivia Martins, would you like to ask a question? I have unmuted you. Okay. Olivia, yeah, let me ask on behalf of Olivia. The question is, it can also used outdoor for glare. Basically, it's asking that can we use this for outdoor glare analysis?
That's a good question. The metrics that I showed, daylight glare probability and spatial daylight autonomy, have been developed for indoor use. They're specific to office environments, and there's some question that we might be able to use them in more extended environments using different minimum values or maximum values for lux level or for glare probability. For outdoor cases, there are a smaller number of metrics that are available, but they tend to look specifically at direct views to the sun or to other reflective objects. So you could use these tools to analyze those. However, in general, those types of simulation aren't as difficult to perform because they're less affected by the diffuse sliding of the space. I hope that answers the question.
Yeah, I suppose yes. We have another question from Hamitris. And Hamitris, I have unmuted you. I can't unmute you. You yourself has muted. Can you just unmute yourself? Hamitris? Okay, go ahead, please.
Okay, first of all, thank you for your good presentation. I wanted to know if you are using the same engine as DIVA in this software, and if you compared the accuracy of the results of this software in comparison to DIVA or not. Thank you.
Thank you. That's a good question. So under the hood, both tools, DIVA and Accelerad, are using Radiance, which is the simulation engine. In the case of DIVA, it's directly calling Radiance routines and then presenting the results from those routines in a graphical interface. For Accelerad, we've modified those routines slightly in order to run them on graphics processors. We've performed some studies that show that we're able to produce equivalent daylight glare probability results with Accelerad and with Radiance. There are some questions that could be brought up about the accuracy in this particular study, because in order to get these simulations to run in a short enough time that we could produce the study bringing each subject in for 1 hour, we had to run on fairly low simulation parameters, low accuracy parameters, to produce faster simulations than we would normally run in an industry setting. So in that case, we might question how accurate the views that the participants saw were, but the tools themselves are capable, given DIVA given appropriate time, to produce accurate simulation results.
Okay, thanks. We have 1, 2, 3 more questions. One from Michael so far. Michael, yes, you can go ahead, please.
Hi, this is Michael Salford. Thanks, Nathaniel, for the presentation. I had a quick question regarding model sizes. Have you found sizes of models that inhibit real-time feedback, or have you made a part of the user interface to allow reducing the scope of the model to be analyzed?
Thanks, that's a good question. One of the nice things about ray tracing is that it's not very sensitive to model size. What it is most sensitive to is the number of rays that are used in producing the simulation result, especially the number of rays involved in diffuse lighting calculations. With AcceleradRT, we've been able to run models that contain literally billions of surfaces. One of the biggest issues with models of that size is not the amount of time that's taken to perform the simulation, it's the amount of time that's taken to load the model into memory prior to running the simulation.
Yeah. We have a couple of questions on whether Accelerate will work on Mac OS.
That's a good question. The answer is that it used to. Unfortunately, it's been, and this is again a commercial issue, that that Apple stopped partnering with DIVA, or sorry, not with DIVA. Apple stopped partnering with NVIDIA some time ago, and as a result, there aren't current software drivers available for Mac.
I have a question from Mikkel Steenberg. Mikkel, would you like to ask a question directly? I have unmuted you. Okay, let me ask on behalf of Mikkel. The question is, thanks, Nathaniel. We use DIVA and annual DTP a lot. Can this speedup also be used for annual schemes? And has any script been written for that yet?
All right, that's a good question. For annual calculations, I've become a big proponent of the multi-phase methods. These are the 2, 3, and 5-phase methods, which are performed with tools from Radiance called rcontrib, rFluxMatrix, and GenBSDF. These are workflows which have produced enormous speedups, speedups of 30 to 50 times or so on using Accelerad. And for those workflows, there can be enormous benefit to using them in in annual spatial metrics such as spatial daylight autonomy, and also in annual glare mapping.
Okay, thanks. We don't have any other question coming up. Michael Salford, do you want to ask any other question, or you are fine with the response?
You just say thanks for the answer for the last question. And the last quick question I had was, have you considered using OpenGL instead of NVIDIA's CUDA for the GPU simulation?
So there are some other recent platforms that might work for this sort of thing. At the time that I started working on AcceleradRT, there was really no alternative. There was an Intel tool called Embry, which had some of the capabilities, but it simply wasn't as fast as the GPU-based tools, even on the GPUs that were available at that time. Today, tools like OpenGL probably don't have that ability, but there are some new cross-platform tools such as Vulkan, which might have some of this capability. The real advantage to the underlying engine that we use, which is an engine called Optics, is that it's completely programmable, which means that although we're using the ray tracing acceleration capabilities of the hardware, we're able to program every part of the ray interaction with objects to make it exactly the same as radiance. And that was really the goal of AcceleradRT.
Thanks. We have there are 3 or 4 questions which are on sky models. And basically they're asking whether any limitations on use of various sky models when we use this.
If you come up with if you find a limitation on a sky model, please submit that as a bug through the website that's shown on the screen. In general, it should work with the standard CIE, Perez, and Utah skies, which are available through Radiance. If there are custom sky models that that someone is using, it might not work with those without additional help.
Perfect. Okay, there's a few more coming. How do you compare your tool with the real-time V-ray rendering?
Sorry, what type of rendering was that?
V-ray. So this again, if I repeat the question, how do you compare your tool with the real-time V-ray rendering?
V-ray rendering. There's always been some question about the commercial renderers which are out there. There is now a CIE standard which allows those developers to verify their rendering packages against some standardized daylighting models. And that can be very useful. The advantage to Radiance, and the reason that we chose it as a model for AcceleradRT, was that it is open source and has been constantly validated and verified throughout its production. And because it's open source, anytime that there is a change to it, we can see what has changed and verify that it still matches the measurements that we would expect to get in the real world. I can't speak to V-Ray specifically because I don't have enough experience with it. I know that there have been instances in the past where a validated tool that was proprietary, that was not open source, would go through some revision, and a new release of it would not meet the expectations that we had from the previous validation. Because of that, we always have to take a gamble when we're using a proprietary tool that new versions of it won't break the validation that we've come to expect. We can do a better job by checking each version to make sure that it's been validated against standards like the CIE standard. But this is really why we why we support open source tools, and why Accelerad remains an open source tool.
Thanks. And we have a last question from Lorani. Lorani, please go ahead. Lorani, can you hear me? Okay, I think finding some difficulty. The question is there some movement towards 360-degree views?
Yes, there has been some work on 360-degree views. I expect if you're asking that question, you're interested in using these tools for virtual reality rendering. There are now some scripts available for Radiance that produce 360-degree renderings and separate left and right eye renderings. There's also a capability in Accelerad, which is available in the current version of AcceleradRT, which allows it to be hooked up to virtual reality view using third-party software. It's still an experimental feature, but it's one that seems to be of interest because there's a desire to have a more interactive experience with virtual environments that people are doing lighting design studies for.
Okay. I think we don't have any other question. I think this was very, very useful interaction after a very insightful presentation. Thank you, Nathaniel, for offering a very wonderful webinar. I request all of you to register for Building Simulation Conference 2016, and also, if possible, I request you to become a supporting member of IBPSA. I thank you, all of you, and Nathaniel again for presenting this webinar. Thank you. I'll end this webinar now. Thank you very much. Thanks, Nathaniel. Bye.
All right, thank you. Bye.